Alright, good morning, Planar Geometry. This is just a little video to help you with the Geometry Sketchpad exploration. Okay, it's not required that you listen to it all the way through. If you're just looking for a particular answer, then fast forward through until you find it, and then grab your answer. If you would just want to listen straight through so that you make sure that you have all the right answers, that is totally fine. Okay, just make sure that you have all of your answers in a separate document and you upload that to the assignment that's called the Geogebra Exploration Assignment. Or Geogebra Exploration question answers. Please put that up on Moodle for me. Okay, so these lovely questions. Number one here, so we were dealing with an orthocenter. Okay, remember the orthocenter is where all of the altitudes meet up with each other, and the altitude is that line that you always knew as the height of the triangle. Okay, it's the line that you draw from one point to the opposite side of the triangle that meets it at a right angle. Okay, so is it possible to have the orthocenter outside the triangle? I think your diagram started looking something like this, and yes, absolutely, it is possible to have the orthocenter outside the triangle. Where is the orthocenter located in the acute triangle? Remember, acute means that all the angles are less than 90. So in the way I have it right here, angle A and angle B are less than 90, but C is not. So I'm going to back it off a little until I have it there, and then I have an acute triangle. Okay, so when the orthocenter is, or in an acute triangle, the orthocenter is located inside of the triangle. Where is the orthocenter located in an obtuse triangle? Well, that's what we just had. In an obtuse triangle, the orthocenter is located outside of the triangle. Okay, and for number 4, where is the orthocenter located in a right triangle? I believe that looks like a right angle right there. And notice the orthocenter is sitting right on top of the vertex. So the orthocenter is located on top of the vertex in a right triangle. And that makes sense because the orthocenter is on the altitudes, and in a right triangle, the altitude or the height is going to be the legs, right? So if this is one of the legs, then this is going to also be the altitude, and so it will go through this point, and then this is a leg, and so it's also going to be an altitude. It will go through this point, so it makes sense that the orthocenter would end up on one of the vertices. If you made a triangle using A, B, and the orthocenter, what would be the orthocenter of that triangle? So A and B, I'm just going to go ahead and scoot A, C inside here so we can see that clearly. So A, B, and the orthocenter are all the 3 points on your triangle. And then where would the orthocenter be of the triangle made by those 3 points? Well, it would be where all the altitudes meet, so let's start looking for some altitudes. So the altitude from A, I would drop it down to the other side until it meets it at a right angle. And it kind of looks like it's going to fall along this line right here. Okay, interesting. So if let's draw the line from B to the other side. So if I draw B to the other side to meet it at a right angle, well, it kind of seems to be following along this line here. And if I go from this vertex to the opposite side, I go along, and it kind of looks like it's this line that's going to meet it at a right angle. So C is the new orthocenter. Okay, so it's just like they swapped places. The incenter. The incenter, remember, is formed by the angle bisectors, the lines that divide the angle into 2 equal pieces. Is it possible to have the incenter outside the triangle? Nope. No matter how you wiggle it, it's not going to go outside of the triangle. So that kind of answers 2, 3, and 4 all in one swoop. Okay, so if it's impossible to have it outside the triangle, then in an acute triangle, an obtuse triangle, and a right triangle, it's all going to be located inside of the triangle. Okay, notice the incenter. They've drawn this lovely circle around it for you. Okay, so the incenter is the center of the circle. In this circle, it meets the sides of the triangle. Okay, it touches the sides of the triangle. So if you remember back from when we did proof, our proof toolkit told us that the radiuses, all the radii of a circle are congruent to each other. So if I draw a radii in this circle, it would go from the incenter and it would go and touch this side. And if I drew another radius, that would go from the center and it would touch this side. I could draw another radius that goes from the center and it touches this side. All those radii are going to be congruent to each other. So that means that this incenter, this point, is equidistant from the sides of the triangle. So this circle tells you that the incenter is equidistant, or the same distance, from the sides of the triangle. Alright, the centroid. So this is all the medians. So remember, the median doesn't have to meet the opposite side at any particular angle. It doesn't have to divide the angles in any form. It just has to touch the opposite side at its midpoint. So it's going to basically touch the opposite side at its midpoint. So is it possible to have the centroid outside of the triangle? As much as I try, I don't think I'm going to get it outside of the triangle. Nope. Okay, so the answer is no. Where is this? So that takes care again of 2, 3, and 4. So if it's impossible to have it outside of the triangle, in an acute, an obtuse, and a right triangle, it's all going to be located inside of the triangle. Can the centroid ever be closer to the vertex of a triangle than it is to the opposite side? That's an interesting question. So I'm trying to see if I can get the centroid to be closer to one of the vertices than it is to the opposite side. Because notice right now it's sitting closer to this side than it is to this vertex. It's definitely sitting closer to this side than it is to the other vertex. It's definitely sitting closer to this side than the other vertex. Well, okay, here's an acute triangle. Same thing still. Nope, not changing much. Maybe an obtuse triangle. Well, no, that's an obtuse triangle, and I've still got this closer to the side than it is to the angle. And what about a right triangle? So if we pull this out like that, still got the same thing going on. Okay, so the answer is no. Okay, and we're going to learn about that a little bit in the lesson. It's called the centroid theorem, and it says that this the length of this side is 2 times the length of this, always. Okay. And finally, the circumcenter. Okay, the most useful one. Is it possible to have the circumcenter outside of the triangle? Yep, it is. Okay. Where is the circumcenter located in an acute triangle? Well, right now this is not an acute triangle because C is bigger than 90. So let me move this around. Well, let's see, that's almost, there we go. There's an acute triangle. And notice as soon as it became acute, it moved inside of the triangle. So the circumcenter is located inside of an acute triangle. In an obtuse triangle, so remember when we had C, let's make that again. There we go. So C is now the obtuse angle in this obtuse triangle, and the circumcenter, notice, has moved to be outside of the triangle. Okay. And last but not least, where is the circumcenter located in a right triangle? Let's make C 90 degrees here. There we go. C is 90 degrees, and notice that sits the circumcenter right on the hypotenuse. Okay, so in a right triangle, the circumcenter is located on the hypotenuse. Okay, and that kind of makes sense because remember the circumcenter is made up of the perpendicular bisectors. So if this is perpendicular, that is going to make them all set up right there. Okay, what does the circle in the sketch tell you about the circumcenter's relationship to the triangle's vertices? So notice the circle is drawn around the circumcenter. Okay, so the circumcenter is the center of that circle. And notice that this circle goes through all the vertices in the triangle. Okay, so if it goes through all the vertices, that means that the circumcenter, same thing that we did with the incenter, if I draw the radii from the circumcenter out to each of the vertices, well, if I draw that radii, it'll go there, radii out here, and a radii out here, they're all going to be congruent to each other. So that means the circumcenter is equidistant from each of the triangle vertices. Okay, so that's what the circle tells us, is that it's equidistant from each of the triangle's vertices, which is why this was useful to us in solving the hospital problem, because it gave us a place to put the hospitals such that they were equidistant from each of the 3 cities. Alright, if you still have questions, please ask. Okay, and this is due by 11:45.